we are starting errors in uncertainties. Actually, uh, you cannot mix the term error with the mistake or blunder. Actually, blunder is always penalized. If you do blunder, you are always penalized. But if you do mistake, you are always penalized. But if you do error and if you report it, then always it's appreciated in physics. It is always appreciated in physics if you do, if you are reporting that type of the error you have there. So error is always appreciated in physics. First of all, we can always analyze the errors. Let us see how we can analyze the errors. Errors can be analyzed. One is the quantitatively. First qualitatively, then quantitatively. So errors are analyzed qualitatively and quantitatively. Qualitatively, errors come in two types. Some are known as systematic errors, and some of them are known as random errors. And when we analyze them quantitatively, what is known as, these are known as uncertainties. If we analyze them quantitatively, then the errors are known as uncertainties. If we fix or we give some value, a numerical value to error, it becomes quantitatively and it is now an uncertainty. There are three uncertainties. One is absolute uncertainty, other one is fractional uncertainty, and third one is percentage uncertainty. So again I say error is something which is you do not do advertently or deliberately, you do not do it. So first one, it is not coming in the board, just I'm writing here, this is the systematic errors, because initially it was not coming on the screen. So errors and uncertainties qualitatively, quantitatively. Qualitatively errors, systematic errors, and then random errors. Quantitatively absolute uncertainty, fractional uncertainty, and percentage uncertainty. Now what are the systematic errors? Actually they are due to the system. Due to the system first. Number two, systematic errors are due to the system, faulty in one direction. Faulty in one direction means they can be either positive or negative. They cannot be both. In single experiment, they can always be faulty in one direction. Actually, these are due to the system. Due to the system. Now, system consists of person performing the practical, lab, apparatus, environment, etc. Due to the system means if a person, actually these errors are due to the person due to his very nature. If suppose something is naturally done, the error which is due to the person very nature, then it comes into the systematic. For example, human reaction time. Human reaction time is not in control. Suppose I have my time is, reaction time is almost, I am old person of 50 years, so my reaction time is most probably 0.4 seconds. So it means that depends. Now if I on and on and off the stopwatch, always I will take 0.4 seconds, the interval between on and off the stopwatch, or I will react after 0.4 seconds. So that is due to the system, fault in one direction. Then they are of constant magnitude. Their magnitude is always constant. And the most important thing is systematic errors cannot be minimized, but they can be eliminated. So these are the characteristics of systematic errors. They are due to the system, faulty in one direction, due to system or person lab apparatus person. These errors are due to the very nature of the person. Then they are of constant magnitude. They cannot be minimized, but they can be eliminated. And examples for the systematic errors are zero error. Suppose an instrument is measuring something, instrument is measuring something when there is nothing to measure. So it's a zero error. If zero error is positive, it's always subtracted from the actual reading. If zero error is positive, you have done your O levels, it's always subtracted from the original reading. And if zero error is negative, it's always added to this one. For example, a wrong calibration of the instrument. These are the zero errors or calibration of the instrument, different environment. Whatever the errors in the system, they come in the system. They have these qualities. They are due to the system, faulty in one direction. Faulty in one direction means they can either be positive or negative. Suppose your watch is slow by 5 minutes in 20 hours in 12 hours. Then always it will be measuring less time, 5 minutes in each 12 hours or 24 hours, whatever the error is. And see, the personal errors also come in random errors. Now personal errors can be, I'm coming on the random error also. Personal errors, I'm just these are for systematic errors, and this we will be doing for random errors. Now systematic error cannot be recognized from the graph. Why it cannot be recognized from the, sometime due to the systematic error, you may have a wrong gradient or you may have a wrong y-intercept. So actually due to the systematic error, I can say a wrong gradient from the graph, wrong gradient or wrong y-intercept. Both can be. So if there is a wrong gradient or wrong y-intercept, if the lines are, if the points are making a line of best fit, but you are getting the wrong gradient or wrong y-intercept, then that is actually the systematic error. But what are the random errors? Actually, random errors are those which occur randomly. You never know that error has taken place. So they occur randomly. Example, its main example is parallax error. Now parallax error happens when suppose parallax error actually is there if you do not see the instrument perpendicularly. For example, if you have this meter rule and you are measuring, if you are not standing right by in this way perpendicularly, you will not get the things right. Suppose if something is measuring like this here, and suppose 5.0 centimeter, when you will see from this side, it will be just coming 4.9 centimeter or less. But if you, so that's always suppose those 4.9 centimeter something, so it will be a parallax error. But if you see perpendicularly, it will always get you the better result. So occur randomly. And example parallax error are personal errors not due to very nature, not due to very nature of the person. Now personal errors, they can come in systematic error, they can also come in random error. See, if the person is doing it randomly, it's not due to very nature. For example, suppose he is counting 20 oscillations and all of a sudden he forgets to count, suppose correct oscillations, that comes in a random error. Or suppose he reads 6 as 9 or 9 as 6, then that's the random error. Or you suppose he takes the reading wrong sometime due to any reason, that it comes a random error. So these are the random error. Now random errors actually scattered graph scattered points on the graph show random error. For example, if you have suppose if you have this line of best fit like this one, suppose line of best fit, 2 point, 1 point is here, another point is here, next point is here, another point. These are nothing but these systematic errors because the points are randomly distributed. So from the graph we can have scattered points when the graph is scattered points, and then we call them that there are the random errors. Random errors are not of constant magnitude. You see, first of all, they are faulty in both directions. Faulty in both directions. It means they can be positive, negative at a time in same practical. Faulty in both directions means they can be sometimes you can read more, sometimes you can read less at the same time. But as compared to the systematic error, they are faulty always in only one direction. Next is see, suppose systematic errors have the constant magnitude, but they have the varying magnitude. Magnitude always varies for the such random errors. And the most important thing is they cannot be eliminated. Cannot be eliminated altogether. You cannot get rid of all these random errors. Actually, they are being eliminated. I think eliminated. Okay. I don't know what the correct spelling of eliminated. I think elimination. E-L-E-M-E-L-I. Okay. They cannot be eliminated. Or you can write. Suppose they cannot be eliminated. You can write eliminated altogether, but they can be minimized. They can be minimized. They are not eliminated altogether, but they can be minimized. So they cannot be eliminated. Sorry, spelling of eliminated must be E-L-I. They cannot be eliminated altogether. They can be minimized by taking repeated readings they can be also eliminated here. I'm sorry, this one eliminated is this one. By taking repeated readings and taking average. So see, these are the random and systematic errors. First of all, I again revise. Systematic errors, they are due to the system. System consists of the person, operator, slave, everything. So if the errors are due to the very nature of the person, then also come to the system. Then they are faulty in one direction, constant magnitude, systematic errors. Cannot be minimized, but they can be eliminated. Example, zero error, wrong calibration of instruments, and there's a wrong gradient or wrong y-intercept of the graph. Now, random errors occur randomly. The example, parallax error are personal errors which are not due to very nature of the person. For example, counting errors are reading 6 as 9 or 9 as 6 or sometimes 8 as 0. Scattered points on the graph, then faulty in both directions. See, this is faulty in one direction, they are faulty in both directions. They have the constant magnitude, they have the varying magnitude. They cannot be they are either eliminated or they remain there, but they cannot be minimized. But they cannot be eliminated, they can be minimized by taking the repeated readings and by taking the average. So that comes for the qualitative analysis. Now I will analyze them, the absolute uncertainty and fractional uncertainty. Now first, what is the absolute uncertainty? Or when we analyze these errors quantitatively, what we get? When we analyze quantitatively, this is an absolute error. What are its characteristics? It must be in one significant figure. It must be in one significant figure, number one. Number two, it has a unit. It has a unit, and it is suppose written if the a plus minus delta a, or a plus minus, you can use this delta also. This is just like that, a plus minus delta a, or a. Now this a is known as the average value, and this delta a, or this is known as the absolute uncertainty. So what are the rules for absolute uncertainty? For writing the rules of writing absolute uncertainty. Rules of writing absolute uncertainty are suppose written a plus minus delta a. So first of all, actually delta a, or which is absolute, must be in one significant figure. In A2 it is allowed for two significant figure also, but in AOS delta a must be in one significant figure. Number two, a plus minus delta a and delta a must have same number of zeros. Same number of decimal places first, and third, or if it's not applicable this, then if it written in this way, a plus minus delta a, number of zeros in delta a must be equal to number of zeros, must be less than or equal to number of zeros in A. It means suppose this has two zeros, then this A must have two or more zeros. It can have two zeros or three zeros or four zeros, but two is not. But suppose this has three zeros. If this has three zeros, then A must have at least three zeros. It can have more also. So I will give how to write the absolute uncertainty in various cases. It must have a unit. For example, suppose how you write this. This one. First I will make this in one significant figure, plus minus how much, this is 0.4, and now this is one decimal place. I'll make this one decimal place, it's 4.9. Actually sometimes one value can be written so many ways. For example, I'm just giving the that example will come and explain. For example, if it's written like this one, so first of all, I would like to express this in one significant figure, so it will be 0.009. Now these are three decimal places, so I'll put three decimal places here. It's 5.39, 6 I have, so 7 or 6 I can, it's up to you. If you retain 6 or you make 7, it's up to you. So 5.396 plus minus 0.009. Or if you wish, this can be more than one way. Suppose I can write 0.01. Now I will write this 5 point, how much, this is 4 and 0. If there are, see, this is one significant figure, there are two decimal places, here are two decimal places, two decimal places, two decimal places, and this is one significant figure. So this is the characteristic of the absolute error. For example, various examples, you should always know how to write a character, the absolute error. For example, if it is this 4.2 plus minus 0.00083. Now I can write this plus minus 0.0008. First I will express this in one significant figure. Now here are four decimal places, but here are one. So I will put 4.200 and 0. Or if I wish, I can write in this also 0.001, and this will be 4.2. Here are three zeros, three decimal places, so this one. So this is the case. For example, and it must have a unit. Suppose it is written like this one. Then what is the absolute uncertainty? Absolute uncertainty here is, suppose this length. So absolute uncertainty in length is here plus minus 0.2 centimeters. And if tens power or something is also there, then it also accompanies with the absolute uncertainty. For example, if suppose L is like this one, then what is the absolute uncertainty here? Absolute uncertainty here is plus minus 0.3 into this also, 10 power minus 3 meters. So that's the absolute uncertainty decimal. Now the second rule is for uncertainty, which is very important, that number of zeros in delta A must be always in number of zeros in A, or A may have more zeros also. For example, if suppose this is the case, how I will do this? First I will make this in one significant figure. 284 in one significant figure will be 300. You know these are not significant. You can take it, but here I am not taking. So plus minus 300. Now here are two zeros, so these two zeros are must. So I will round it off. This is 4, 3 and 9. But here can be more zeros. For example, if I write in this way, how will I write? This is plus minus 300, and now here two zeros, there are already two zeros here, so 4, 6, 000, but here can be more zeros. I give an example. For example, if something is like this one, I will do this. First, this will be plus minus. See how it this I can write this 0.96, so this will be plus minus 1. Now clearly this is plus minus 1, no decimal place, here must be no decimal places, so 10 plus minus 1. Now here are more zeros, here no zeros, okay. Here can be more zeros than this one, but number of zeros in here must be this one. For example, 6, 4, 3, 8, 6, 9, 4 plus minus 2, 8, 6, 7. How can I make this in one significant figure? This must be 0, this must be 0, this must be 0, and this is 8, so this must be 3000. And now here these are 3 zeros, so these must be zeros, 0, 0, 0. Now this is 6, so this must be 9. Now 3, 4, 6. So in that way we can have the absolute errors. In that way we can have the absolute errors. Now let us see what the fractional uncertainty is. Fractional uncertainty we define as plus minus delta A upon A, and it will have no unit. For example, if something value is like 6.5 plus minus 0.2 centimeters, then here I should tell another thing also. Here the maximum value should be, maximum is 6.7 centimeters, minimum value here is 6.3 centimeter, and average is 6.5 centimeter. Absolute error is plus minus 0.2 centimeter. Now what is the fractional uncertainty here? Fractional uncertainty here will be is plus minus 0.2 upon 6.5. Now centimeter is cancelled out, and now you can have this in up to one significant figure or two significant figure. There's no restriction how many significant figures you are taking. Suppose actual value is coming actual value is coming 0.030. I'll write this in plus minus 0.308 after three significant figure. It will have no unit because the centimeter cancel out. If tens power is there, it also cancel out. Suppose I have to find fractional uncertainty here, then I write plus minus 0.2 into 10 power minus 3 upon 6.5 into 10 power minus 3. this cancel. So it is usually, if tens power is there, you can always get the fractional uncertainty just dividing this by this. Then what is the percentage uncertainty? Percentage uncertainty is just 100 multiplied by fractional uncertainty, this one. So percentage uncertainty, in any case I can say delta A percent will be always equal to delta A upon A into 100, means fractional uncertainty. This can even be three significant figure. For example, the percentage uncertainty here will be 30.8%. So these errors are analyzed in that way. Now we will see how these we can add, subtract, multiply the errors. That will come in my next lecture.